So, good morning to everybody. Thanks that you've been joining this GNF panel discussion here, dealing with the topic asteroids. Are they a threat or an opportunity? And I will briefly introduce our panel participants, starting from the left to the right, I think. So we've got Fritz Merkel, former member of the management board of the OHB SE, with subsidiaries in multiple European countries, also here in Bremen, also Luxembourg, which might be relevant later on. We've got Jakob Bross from the Czech Republic, from the university there, dealing with a lot of aspects on asteroids, also on the utilization of asteroids later on. We've got Patrick Michel from the Observatoire de Côte d'Azur, I would say the leading scientist with regards to asteroids in Europe, and Ian Carnelli from ESA headquarters from Paris, managing all the ESA activities related to asteroid missions, mainly in the domain of asteroid deflection. And I would like to start with Patrick Michel, maybe giving us a brief introduction on what are asteroids, what do we know, what don't we know.
Okay, so good morning, everybody. So asteroids are the remnants of the bricks that form the planets. And contrary to planets which are very big and therefore experienced heating and their composition, chemical composition, was transformed by the heating, asteroids are small enough that they kept the memory of the composition of the solar system. So most of them are between Mars and Jupiter in a belt called the asteroid belt. And they evolve collisionally, and now they are eroding little by little. They disrupt each other. And some of them are put in a trajectory that bring them close to the Earth. And these are the subpopulation that we call the near-Earth asteroids. So most of them come from the main belt. And they have one advantage and one drawback. The advantage is that they are easy to access with space missions because they come closer to the Earth than going between Mars and Jupiter. But because they come close to the Earth, the drawback is that sometimes they fall on us. And so they represent both an opportunity, science opportunity, a mining opportunity if you are interested in resources, but they also represent a threat. And this is, I think, something which is important because we have many natural risks in the world. This one may not be the highest one, it's actually one of the lowest ones, but this is one that we can predict and prevent by means which are reasonable and feasible, but that just need to be implemented. So we have a diversity in terms of composition, etc., and we are still at the beginning of understanding them. And one of the good examples is Ryugu from Hayabusa 2, which properties are totally different than what we expected. Because they are very diverse and they are very hard to characterize from the Earth. So we need to go there to be able to better understand what they are made of. And also the big challenge that they have a low gravity, so the way the surface behaves in this environment, very different from the Earth, is something that we just start to beginning to understand. So we have to, and so to finish about that, is that even though we don't know much about them, we need to do space missions to better understand them. And in fact, whatever the mission you do, whatever objective it is a planetary defense objective or science or mining objective, you still need the same kind of information. So we should push for any kind of asteroid mission because whatever is your interest, the knowledge will be extremely valuable.
Yeah, thanks a lot. Maybe I might ask an additional question. Maybe you can explain the difference between an asteroid and a comet.
Okay.
As we had this Hayabusa mission going to an asteroid, not so long ago we had Rosetta and Philae going to a comet. Maybe 2 sentences about what is the difference.
Okay, so before a few years ago, the distinction was clearer than now. So before, we understood that the asteroids are these rocks which do not have an activity. An activity is, for instance, if you have ice on the surface and it comes close to the sun, the ice sublimates, and you have this beautiful atmosphere and coma that characterize a comet. And therefore, the comet is the other way. It's an active body with a coma, etc. And the reason why there was this distinction is because asteroids are close to the sun, up to Jupiter orbit, where the ice is naturally stable, so they are non-active. And the comets evolve in the outer solar system, are formed in the outer solar system, and therefore they are full of ice and volatiles which can sublimate. And then asteroid would inform us about the formation of the terrestrial planets, because they are closer to the sun, and the comets would inform us about the outer solar system initial evolution. Situations have little changed because recently in the asteroid belt, we discovered asteroids also have an activity. So we don't understand yet what it is active, whether it's an impact and it's just dust, or whether there is a volatile. We also discovered ice on the surface of some asteroids like Threaths and even Ceres. So now there seems to be the frontier is less sharp. There seems to be a continuum in terms of physical properties between asteroids and comets. Actually, some models made in Nice say that the asteroids which are carbonaceous, which are actually between Mars and Jupiter, come from outside Jupiter orbit when the planets danced initially at the origin of the solar system. So the distinction now is less clear in terms of physical properties. However, dynamically, we still have the distinction because asteroid belt is, the dynamics is well characterized. They are circular orbit, low eccentricity, low inclination. Near-Earth objects cross the trajectory of the Earth. Comets have different kind of orbits, but that's the only difference I would say. The last thing is that in terms of threat, comets are representing a very small portion of the near-Earth object population, maybe between 4 and 6%. The only threat which cannot well be characterized is long-period comets, because they come once in the solar system, and usually you discover them when they pass Jupiter. So it's only a few years before they come close to the Earth. But the advantage is that they have a very high inclination, and therefore the likelihood that they intersect the Earth when the Earth pass where they are is very, very small, fortunately. Sorry to be long.
Okay, thanks a lot for that. This was already going very deep into detail on what do we know on asteroids, what do we want to know in the future, why do we want to know, but from this, let's say, scientific perspective, the pure interest to better understand them, their origin, and maybe also the origin of the solar system. But I would like to hand over to Ian, maybe a few words on the agency's perspective on how to deal with them, not from the science perspective, but maybe from this perspective, what could we do if there is a risk of a collision between an object like an asteroid and Earth?
Good morning, everyone. Thanks for the question. We're basically working on a very boring subject. We are actually buying or preparing insurance for planet Earth. Like when you buy a car, and before you actually buy a car, you buy an insurance. And that's what we're trying to do at the European Space Agency, and together with JAXA and NASA and other international partners. So this insurance policy is basically a mission. As Patrick was saying, the asteroid hazard has the benefit that is the only natural hazard we can prevent. And today we are in a very interesting situation where we think we have all the technology we need to prevent the impact from an asteroid. It works on the simulations, it works on the paper of our industrial studies, but we've never tested it. And the point is, the moment we identify incoming asteroid, that would be too late. You need to have the technology ready and tested before the threat is identified. So that's what we're working on. We started in 2002. So the story is quite long. I will not bore you with the whole story, but this is to say that it's not something we have invented yesterday. Today we're working on a very concrete concept. The mission is called AIDA. It's a partnership between ESA and NASA. NASA will launch a spacecraft. Now it's been approved, so in June 2021. And it will impact the moon of a binary asteroid. So it's an asteroid with a little moon orbiting around it called Didymoon in October 22. So I invite everybody who's in the room in 22 to look for observatory. Maybe Patrick will invite you all to observe in Nice. It's a nice place to observe this impact. It will be visible from ground, and this is the test. This is the insurance policy we want to put in place. They will demonstrate, first of all, that they can hit an asteroid which is 160 meters in size. If you go back to an image of Ryugu, you will see on the northern hemisphere a big boulder. And that boulder is approximately the same size of the target of this experiment. This tells you how small it is. So from industrial engineering point of view, it's a big challenge. What we want to do is to get after this impact and collect all the physical and dynamical properties of the asteroid, and even more so to see the crater, so that we can get all of the elements that are needed to validate the numerical impact codes. And by doing this, we would have our insurance policy. So I think it's a very important moment in our history. We've seen the success, or we are enjoying the success of Hayabusa 2. As Patrick has said, every mission to asteroid tells us a lot about these different worlds. We need to keep exploring these worlds, and it's a moment where we can build on the heritage of Rosetta, all the technological heritage we have built in Europe, the technological and industrial competence we have now in Europe for small missions in deep space, and other technologies related, for example, to close proximity operations. There are many challenges related to how you move or how you operate around such a small body. Let's not forget that these bodies have virtually no gravity, which is actually a very interesting engineering problems for companies that are interested in resources utilization. So even by doing a planetary defense mission, we will learn how to interact with this body, we will learn what they're made of, what is their structure, and that is valuable information to one day design anchoring systems, digging system, to actually extract material and process it. Sorry, I made the story long, but that's what we're working on at ESA with our industrial partners.
Yeah, thanks a lot, Ian. I think making the story long is, I think, absolutely adequate here, because it's not a simple topic there. And I think you raised 2 points which we might pick up later on: this insurance policy, legal framework, and also the technologies needed. But before we go to the last 2 speakers here, I would like just to inform you that if you downloaded the IAF app on your smartphone, you can ask questions or type in questions here as well, which we show then on the screen, and we'll try to answer them. So if you're going to the IAF app, at the bottom of the menu, you find Ask a Question, which will then be displayed here on the screen later on, but maybe that you're prepared for that. But getting back to our panelists here, maybe Fritz, you can tell us a bit about the perspective of the, I would say, classical industry on this asteroid topic. So maybe on the hazard aspect of the asteroid, but also maybe a perspective on the opportunities, on the potential utilization of asteroids, as OHB is located also in Luxembourg, and Luxembourg has somehow claimed to be the European country to foster the usage or the utilization of asteroids.
Yes, good morning, ladies and gentlemen. Yeah, so we got a very good introduction with which bodies we have to work with and to visit and to encounter. And Ian, you said clearly what is the intention of the agencies to do it, to go there. But in order to materialize it, one needs industry, because someone has to build the equipment for the astronomers in the early detection, in the monitoring of what's going on. One needs equipment then to come close, to approach, to survey, and to deflect, or to mine on, to take it apart, etc. So this is on one hand from a traditional approach, where institutions like agencies like ESA, like NASA, would approach industry and ask them to do it. But we all heard these are also potential fruits of our universe, so it immediately triggered also an interest in industry, in economy, or by investors to say, if these are new resources one may need later, in particular, if these could be resources in the future for deep space missions, then it is a commercial case, and it's out of what usually an agency or a governmental institution should do. And clearly that's where we are from industry very eager to be involved from the very beginning. As you said, I think The technologies in principles are there. From the physics, there's a lot of understanding, but we have to survey more. We have to know what is the surface. Are they all similar? Because when you approach a nearly zero gravity object, you have to know how you can grab it. Do you just get with your harpoon into dust? Or do you go into metal or solid rock or whatever? So how it is, how are they the same? Or when you approach, at what moment does one know what object it is, so which technology to apply? You cannot have a trunk full in your satellite or space vehicle to be prepared for all eventualities. So I think the surveying, monitoring has to be extended, and this can be done. Novel detectors have to be applied to get more information. Clearly, we have to learn and to advance more in the propulsion, and then also to first, in a reasonable time, approach them, but then also to slow down, and then to circle around, to monitor, etc. And then landing technology, approaching technology. What Mascot had demonstrated now, and first sensors on an asteroid, I think will give us a lot of information. So what came out within a few hours where Mascot was alive, I think it will keep astronomers and experts busy over months and years in order to learn more. And industry is ready to be a partner in this early phase, but industry clearly is highly interested to be there in the future, to see this as a novel enterprise, and in particular then as a source of resources in several decades for future space missions. At the moment, at least my personal feeling, to bring these resources, metals or whatever, to ground, to Earth, I do not really see a need. If we're a little bit more careful, our resources are fully sufficient, what we have on our planet. But if we do something, manufacture in space, manufacture for space mission, get fuel, etc., then it is, it will become an economic factor, but maybe when we are with a stick or in a wheelchair approaching, say, a conference in 20, 30 years, maybe not me, but the younger ones here, we hear about the success of this. Clearly, we are just in the beginning of exploring space. Compared to, let me say, exploring our planet. We are just a little bit behind Columbus. And so the question is, how does it develop in a few years and in the next decades?
Yeah, thanks a lot. Also, this comparison to Columbus is, I think, a nice anecdote somehow, and showing the, let's say, the astronomical time scale, what we're talking about. And I would like to combine your last parts about the utilization of asteroid resources, maybe combined with what Ian brought up at the beginning. You called it an insurance policy. I would expand this a bit to the legal framework, and maybe Jakob could elaborate a bit on this. What are the perspectives for utilization of asteroids, or what the opportunities are, and what is needed to go there, not to go there physically to the asteroid, but to achieve this utilization at the end?
Thank you very much. Good morning, everybody. Well, that's exactly, I really like what other speakers said, because there is definitely a lot of opportunities within the asteroids as we are speaking about resources utilizations, but we are just on the starting line, and right now all the scientific missions of ESA and NASA are the pioneering ones that are helping to develop the technologies necessary for getting the resources in the future from the asteroids. And it's great that there is already the collaboration between the industry and the agency, because it should be like that. It is great that there are many private companies developing their own technologies, and that there are many scientific missions of the agencies, but it's about fusion, about fusing the capabilities and know-how and experience. In that case, you can get there way sooner if the collaboration is successful. As for the regulations, and legal framework in case we will be able in the coming decades to really get resources from asteroids. That's going to be, I think, even more difficult than the technological aspect of it. It's, it's not that big problem to develop the technology and test it, but it's a problem to get the consensus among many countries and many players and stakeholders that are very interested in this area. And it's great that already some things are happening. Apart from the discussion within the United Nations responsible bodies, there is also other entities like Hague Working Group, for example, that are looking at the resources utilizations and the legal framework and how to frame it and how to approach it within current international legal framework. What we do at the Charles University, our research team there is exactly focused on the planetary defense from multidisciplinary perspective. So it's not only about policy, it's not only about law, but we got also engineers on our team, we got astronomers on our team, and even though our aim is to have a research report for our government, it's going to be about to advise how we should contribute on the international level, because it's critical to approach these issues on international level. It's a global problem. It may be a global problem if an asteroid approach Earth and it will be on a collision course. And as for the resources, it's also a global opportunity. The resources in space should be utilized sustainably and in a way that it could benefit all the mankind on planet Earth. So that's important not to focus on national policies and then argue with the other participants, but it should be, let's talk from the start how we should do it collaboratively to achieve something meaningful.
Yeah, thanks a lot. I think Fritz wants to add something on that.
To complement on this, in particular, if we look into mining resources utilization, one needs private investment. Huge amount of money. So clearly, this shall not be a public thing, it has to be a commercial item. But to get investment requires clear legal, regulatory boundary conditions. Nobody would give money into an endeavor where he does not know what are his legal rights. And in particular, it has to be internationally agreed. And what you said, Sarah, these international committees, and I think that's very essential, because otherwise there may be the risk that now national regulations are used already now to influence later competition. That means declaring what is my property, what is yours, can I kick off for my asteroid, or do you have the same right? So it is very important. Regulations are internationally agreed, nevertheless, they only apply through national regulations. And there is a very important issue.
So maybe...
Yeah, I just want to say a word about the regulation. If it takes time, you have time, because for the moment we need to learn much more about these bodies. I mean, each mission that went to an asteroid turned our understanding on its head. And that's the case for Ryugu. Ryugu has not at all the properties that we thought it would have. And I belong to the team of Hayabusa 2, I belong to the camera. I'm co-I on the camera, I receive images every day, and every day wow, what is that? And so that's one thing. So we need really to go see more bodies, because we have a great diversity. Their properties are very different, and something which misses sometimes, that's not the case for Hayabusa 2 and soon OSIRIS-REx, and it's very important to always have this component in these space missions, is an interaction with the surface. Because when you look at an image of an asteroid or even on Earth, you look at the ground, if you don't touch it and you don't know whether it is you have different interpretation. You need to know whether it's crushable, whether it is soft, whether it is hard, and unless you interact through an impact, through a lander, through a sampling mechanism, you cannot know. I mean, it can be very misleading, especially in a microgravity environment. For instance, if you ask me, based on the images of Hayabusa 2, will mascot bounce? I would have said yes. Actually, we did modeling, and the bouncing was quite high. And in fact, he didn't bounce much. So it's a good news, but it's also a great mystery scientifically. We don't understand yet why he didn't bounce as much as we thought. So that's why I think, the road is still long before being able to control well the interaction. We see when we think about the sampling mechanism we want to put on a mission, It's a nightmare because you have to deal with the budget you have and the uncertainties. So you need to design a sampling that can cope with many kind of surfaces, because unless you have a precursor mission, you don't really know what you will have. And another thing also is that if the private companies start to do missions to asteroids, I strongly recommend that the data remain public for now, because we still need to improve our science knowledge. And that's not necessarily the scientists who speak, it's practically. For the companies, they want to have a benefit from their mission, they need the scientists to tell them how this works, because even the scientists themselves don't understand. So that's an important point.
And it has to be public, because with mining, maybe you deflect the asteroid and it becomes a killer asteroid. And that is the question is out. But what you said, it's like, is it billiard or softball to deflect?
Okay, yeah, thanks.
If I can hitchhike on this, I think the role of space agencies at this moment is to combine industries in the development of these small spacecraft. I think one thing is to do huge scientific missions, Nobel Prize, fantastic science, fully support, and we should do more. On the other hand, we should start doing small deep space probes and develop these technologies which are still on the edge of being there, but we need to validate and we need to learn how to do autonomy, because this, if you want to interact, you cannot do full manual control, and these are technologies we still need to develop. And so I think there's this dual use or dual perspective, and I think there's still a moment when we can work together and bring industry to a point where they're mature enough to then go and start interacting with the asteroid. The other aspect I fully share with you, the advantage of a planetary defense mission is that in this case we can make the data available right away. So with Hera, I would be, we can share images right away after we get there, and all of the data will be absolutely public. And I think this will be also the engineering data will be vital for those companies who are planning to do in situ resources utilization.
And I think it's critical that Europe gain this expertise with autonomy, etc., because we see that JAXA, Japan, US are, going in this field really fully. I mean, you look at the asteroid missions at both NASA and JAXA, they have a roadmap and they gain the knowledge. And since all these business, I was going to say, but this science, planetary defense, mining, is an international affair. I mean, Europe has to have also a leadership with all these two main countries and maybe more in this field. So really need to push in order to have these kind of missions which serve different communities with different objectives. They need the same knowledge and they need the same industrial and technological expertise. We cannot leave that. Even though my American and Japanese colleague invite me in their mission, which is great, and I'm fully grateful, we also need the Europeans to have this knowledge. And moreover, we also know that these kind of missions are a good trigger to inspire the young generations. And when you give public talks, I'm sorry to say, but it's much more exciting to talk about a mission that goes to see a new world than to talk about a telescope that just look at stars. Even though you have Nobel Prize with that, if you want to inspire young generations, you should invest on these kind of missions. And even my cosmology people may say, yeah, but it's not our science. No matter, I had students who came to me because they were excited by a public talk, and eventually now they do cosmology. It's just a way to inspire young generation for the knowledge, the curiosities, the challenges. And it's true, it's much easier to talk about these kind of missions because we have images of new worlds than any other kind. And it's not at all pejorative, of course.
So maybe, I think Fritz wanted to comment on this, but before I would like to use the opportunity to say we received a lot of questions from the audience already. Okay. So and I would maybe, after your point, if you don't mind, switch to the questions from the audience, maybe grouping them somehow according to topics, so that we use the remaining time to answer these topics which are of interest for the others. But before this, please, Fritz.
Yeah, so what you said, involving the next generation, young generation, very essential. And this has to be the bridge, because you said in US or in Japan, China, we do not yet so really know, but it is a different approach. And I think behind this is the way how politics sees this. I think in Europe, in Berlin, in Paris, and many capitals, except Luxembourg, as asteroids is seen as something crazy. We have many more other problems. So there is not a strategy to prepare something which at the end may take 20, 30, 50 years to bring it into operation, a defense system, a mining expert. Politics often thinks only in 4 or 5 years terms for the next election. And so it's very important, I think, in particular for asteroids, to have the bridge between population, young populations, politics, because what ESA can do, what you can do in your science institute, comes always through funds politics has to release. And if we look what, let me say, the economic factor and the security factor are not really seen as an urgent issue, as something others can do later, and the next politician thinks again. So I think others may pass Europe in this. So I see there an important point. On the other hand, one can only congratulate our Japanese audience here and the US audience that their politics is more visionary on this, and yeah.
But I think just to comment on that very quickly, the industrial lobby is important because as a scientist, I mean, I cannot complain because you see DLR, CNES, they do bilateral, and we have small body missions for the scientists to play with. The pity is that we don't have it also in Europe. I think it's a great move to work with our Japanese colleagues. I love international collaboration, so I'm very grateful that CNES supports me in this kind of missions, and not only me, by the way. But what I would like is that also we have the European industries developing this expertise, and we also know that a European mission federates much more the whole small body community than mission done elsewhere where lucky individuals like me are involved, but it's not the whole community. We share the knowledge and the expertise.
And it's not just the community. I mean, we see with Rosetta what they do with the public.
Exactly, the
and
European
with the young
public
generations.
identify more to European mission also. So I think we need both. We need to have other countries doing the mission, inviting people, but you also need to have our European industries and people getting this expertise.
Yes, thanks a lot. I think the last point is absolutely valid. So it's not just about technology and, let's say, commercial interest, but also international collaboration and, as Ian just said, attracting the public like Rosetta and Philae did, as Hayabusa and Mascot did just 2 days ago. And I think also the motto of this Congress, involving everyone, should bring us to the point that we really bring on the screen the questions from the audience. Maybe I select some of them or group them a bit. So maybe I would start with one which is dealing with the beginning of this panel, let's say properties of asteroids and so on. So maybe, Patrick, you might be the one to answer those. So the first one then would be, for example, I hope this works right now as it should. Yes, it does. Are there asteroids which have sufficient water for future human expansion in the solar system? You addressed this already a bit in the beginning, asteroids, comets. Maybe you can answer on this.
Yeah, that's not an easy question because so what we know about asteroids in terms of composition come from spectral observations. So from the Earth, unfortunately, the data are very limited because the asteroids do not generate their own light like a star. They just reflect the light from the sun, and it's reflected from the first micrometer from the surface. Plus, in general, it's average about the whole surface because these are star points, light points in the sky. So we know from these spectral observations that some of them have what we call a hydration band, meaning that the material saw the water. There is no water anymore, but it's altered aqueously, as we say. So it's all the waters, and it's very difficult band to detect from the Earth. Luckily, we know that we have some bodies in the main belt which also have ice on the surface. We don't know how it's stayed there because it's normally unstable. So there are some water there. The problem is it's not like you go and you take a glass and you fill your glass with water. You need to recombine hydrogen, oxygen, all this, because it's aqueously altered, but it's not really water anymore. So there are ways probably to do that. People are working on that. And there is the material to do it. The actual amount is still uncertain. We believe that some of them have 20% based on the comparison with some carbonaceous meteorites, 20% of alteration. But it's just a scientific number, and scientific number have huge error bars. It's not, well, although finance has huge error bars, but so now to say that which have sufficient water for future human expansion in the solar system, then that's a technological question. How much we are able to extract the component that make you transform this into a usable water, and that's still to be worked out.
Okay, thanks a lot. I think the last part brings us in principle to the utilization of asteroids, but before this I would like to bring up those questions which are related to the threat of asteroids. So let's see what we have there. So one is here right now, so this would be, can you elaborate on the different possible threats depending on the NEO's type? So really focusing on what is the difference, or what are the different NEOs we know, and what are the different threats resulting from them?
Well, in fact, if I want to summarize, I mean simplify, I would say you have two populations in the asteroids: the one which are bright and the one which are dark. So we classify in two distinct classes: the one which are carbonaceous asteroids, as we say, low density, and the other one are silicate-type asteroids. They certainly behave differently if you want, for instance, to deflect them with a kinetic impactor like DOT, and then ERA wants to do. But in terms of threat, like statistically, how many of them come to Earth, depending on the type, it's sort of random. We don't have any... The interesting thing, though, is that when you look at meteorites, although we have about half the population which is carbonaceous and the other half silicate type, silicate rich, in terms of meteorites, you only have 5% of the chondrites which are carbonaceous. So there seems to be a bias against the arrival of carbonaceous material on Earth, and one potential explanation is that this material is too fragile to go through the atmosphere, because the abundance is about equivalent in space. And thanks to Hayabusa 2, which by the way is in a carbonaceous body, maybe we will see that it will collect something which we don't have on Earth, because it's too fragile to come. But otherwise, I mean, what will be the next impactor, if you ask me? It could be silicate type, it could be carbonaceous type, less likely a metallic type. We don't have that many. So.
Okay, thanks a lot. So coming closer to this topic of asteroid deflection, how can we protect ourselves? Ian already raised, okay, insurance policy, whatever. I've got two questions which maybe we can raise here combined. So one is what magnitude of velocity change is required to deflect an asteroid from an Earth impact trajectory? And the second one, or maybe also there might be three. The second one then might be, what do you think is presently our minimum response time in case of a real threat? What are realistic means to reduce it? And the third one, where is it? It refers to the cost. There was a question about what is the cost of a mission like that. So if I find it, I will put it on the screen, but maybe we can already start discussing the first.
This is a very good question, to be honest. I'm always amazed by how prepared the people are. So the funny thing is that to deflect an asteroid, what kind of velocity change? It's very small, 0.5 millimeter per second. That's enough to deflect an asteroid. So, but the key answer is actually, when do you do it? That's really the key point, because the amount of deflection you need depends on the warning time you have. So if you have many decades of warning time, the deflection can be very, very small, because then it accumulates over time and the trajectory changes dramatically and it misses the Earth. If you only have a few days, the only thing you can do is call the civil protection. So that's why, first of all, it's very important to have a good ground-based survey system. And as ESA, we're developing a network of telescopes that is complementary to the one in the US. It's called Fly Eye telescope, and these will monitor the sky every night and look for the approaching impactors, so the small asteroids like the ones in Chelyabinsk. On the other hand, yes, we need to be able to build our warning time as much as possible. So the minimum depends also on the insurance policy I mentioned before, because clearly, if we were just to wait until we one day discover a threat, then we would have to build the whole system from scratch and possibly maybe do a rehearsal, and then we would need a lot of time. If we are able to finally implement DART and HERA, that means we also have a design, a proven design. We can rebuild such a system, and typically, in that case, a couple of years would be more than enough. So that's why it is important that we have this planetary defense test, so that we have not only the capabilities, but we also have, let's put it this way, the design. And the kinetic impactor, which is the technique we want to test, is also a very flexible one, because it works for asteroids down to maybe 50, 60 meters, up to a few hundred meters, which is actually the range of asteroid size that has the highest probability of impacting our planet. Maybe one thing we should also say is that the kilometer size asteroid, we believe, or they believe, and I trust them, that we know more than 90% of them, and none of those big guys are heading towards our way. We have we can propagate the trajectories fairly accurately, and we know that they don't pose any threat today. But the small ones, we know a very little fraction of them, and that's why it's so important to test the kinetic impactor. Now the question is, as Fritz, you were also saying, the politicians typically look into their terms, 4 or 5 years, maybe 6 years sometimes, and this is a low probability. So should I really invest all of this money? So when I give public talks, I always have a couple of slides on this. The cost of the, okay, first of all, implementing this insurance policy, doing AIDA, between ESA and NASA has one major advantage, is that we only pay half of the insurance policy, because NASA would do one part and we would do the other part. If we were to do it alone, it would be twice as much. So here we have really a unique opportunity to save cost. In an international frame, because let's not forget that planetary defense needs to be an international endeavor. Now, the second thing I say is the cost of the mission is equivalent to building, for example, a new Formula One track. It's 260 million euros. That's the cheapest Summer Olympic Games in the history of mankind, which was in Tokyo in '64. And to give you an idea, the Summer Olympics in London were 12 billion. 262 euros are 34 cents per European citizen. So that's how much this insurance policy would cost.
Yeah, thanks a lot for this example.
And by the way, if I want to add something on this, because the first time I was asked this question was when there was a deep impact mission to a comet in 2005. I was on radio, and I was answering question in live, and one guy said, well, aren't you ashamed to throw $300 million on a comet? And I said, well, that's not exactly how it works. These $300 million are used to pay salaries of people who develop the mission, to pay industries, to train students, PhD students, engineers, postdoc, researchers. So it's not like we put the money in a spacecraft and it goes and it burns. It's actually used to pay people, to train them, to make them gain expertise, etc. So it's part of every spending a government does every day. Just the purpose is not to build a stadium or something like that. I mean, the stadium in Nice costed 3 times HERA. So, but I mean, at the end, the money is used for the same thing: salaries and in addition, a gain of expertise.
And innovation and technology,
Exactly.
which can be used for very different other aspects.
Yeah, thanks a lot. So I would like to get to this aspect of international collaboration between industry, science, and so on. And I think we've got a couple of questions there. 4 are here on the screen right now. So is there any working group, international committee that brings together lawyers, policymakers, researchers, and engineers to draft the first policy guidelines? Second, how can we better spread the cost? We already addressed this topic a bit, to buy down the asteroid impact risk so few countries don't carry too much of the burden. How do we increase collaboration between scientists and industry? And the 4th one here is either industry or scientific research centers working together with the UN on this topic. This is an international matter that must be globally tackled. So maybe, Jakob, you can
because
some of those.
The next generation or the young generation has been mentioned here a couple of times during the talk, and I'm glad that it was by my much more distinguished colleagues. There is actually the organization I came from, the Space Generation Advisory Council, which is just a really amazing organization bringing together young professionals and students from all around the world. We have like 15,000 members. And we have project working groups, and one of the project working groups is called Near Earth Objects, and it's focused exactly on this topic. And it allows us to work together along with the experts from the agencies, because ESA and NASA are our partners, and with the industry as well, that is also heavily engaged, including companies from Europe and America. So it's one of the opportunities for the young people to be really engaged, to really discuss these topics, this particular topic, with the subject matter experts, and draft some proposals, because we are a permanent observer at the United Nations COPUOS, and after our work, we can propose some suggestions or some proposals to it. So that's one thing. And then on the national levels, but with the international, let's say, impact, I already mentioned, for example, our research team that is collaborating with many partners from around the world, from Europe and United States as well. So that's another opportunity how to bring together all these different stakeholders that sometimes have different goals, different opinions, and it's critical to make them talk together and to find some agreement on it. So.
If I can add something to answer directly the question, there is now at the United Nations some actions. There are 2 groups which are now working. One is the International Asteroid Warning Network, which actually is a group made of scientists, observers, and which try to have an alert system and increase the discovery of these bodies and have a way to communicate to the media and the public when there is a warning or something. And also they report to another group, which is called the Space Mission Program Advisory Group, which is represented by the space agencies like ESA, NASA, even China, JAXA, and other agencies in the world, and which this group is aimed at defining what are the proper response, international response, in case something happens. So it started only a few years ago. It takes time, you know, bureaucracy, because this is pure bureaucracy. I mean, well, anyway, it takes time, but at least these groups exist. I contribute to the I1 in the steering committee. I go to the SMPAG. I always push to say, okay, it's good to write reports and say we need to do something, but we have also to implement some tests. And then on another level, because you talk about scientists and industry. So first, in science, there is no frontier. That's great. You have Hayabusa 2, for instance. Take Hayabusa 2 and OSIRIS-REx. OSIRIS-REx is a sample return mission by NASA. It comes after Hayabusa 2. You know, usually the Americans like to be first. In this case, it's fantastic. There is an excitement of the OSIRIS-REx team to what the Japanese are accomplishing first. Some people, like myself, are in the 2 teams. There is an overlap, and we exchange ideas, exchange knowledge. So science has no frontier, and it should remain that way. The interaction between scientists and industry is also improving, I would say, because particularly in Europe, usually there is a sort of frontier imposed by agencies to talk directly with industries. But now I think it's improving. It's very interesting because we don't have the same culture. I always remember the first time I went to Lockheed Martin for OSIRIS-REx, they told me, okay, what is the size distribution of the grains on this body for our sampling mechanism? They say, oh, we don't know that. So of course, the industry, they need to build something that works. They need actual numbers, and we are not used to get the actual knowledge they need. So it took time to be able to be familiar with a different way of working, and now I think it's working, and it's fascinating. It's very important because at the end, I mean, these are the engineers that need to succeed for us to do the science. I would say we have the easy part because we analyze the data, but the data are acquired by these people and the people who built instruments. So it's very important to improve the interaction between these scientists and industry, and it's coming.
Maybe if I can add one thing, is what we're testing together on HERA, and it's the first time where we actually put industry, ease on our case, and the science in the same team. So we don't work anymore with interface documents, but we put everybody in the same group and producing. So all the scientists are invited to the meetings with industry. And so how can we improve? I think we're testing new ways of working and co-locating and different topics, and you bring different expertise and you put all the brains together.
And I can witness that this is great because I can see also the engineers. Sometimes, I mean, I don't know why I heard that. Well, you know, they are engineers, they don't need to understand the science, but they are interested also. And on the other hand, I am interested also to know how the instrument, the satellite will work, etc. So it's much better when we are together and we exchange our knowledge. It's what's fascinating. Okay, we are the same team, basically.
Yeah, thanks a lot for that. So I think we heard a lot about the threat of the asteroids, the activities to mitigate them, asteroid deflection and so on. There's a couple of other questions regarding this on the HERA mission, on ways to mitigate the risk, but I would like to make use of the remaining few minutes we have to focus a bit on this asteroid mining, the utilization aspect. So I would bring on the screen now a couple of questions regarding to that.
Maybe in between there was a question on how to get all worldwide, let me say, to carry the burden on it. I have no idea. I think it's the same question could be applied to space debris. Who pays for removing space debris or mitigate space debris? There really, I think, innovation has to come, how this could be done on an international basis.
I think the advantage of planetary defense is that it's not a continuous effort.
Yeah.
Maybe that's from the economic point of view. You don't need to put in place a system that keeps working for years to clean up
exactly.
something.
Yeah.
Planetary defense, you really need to put the tools, demonstrate they work, and then you're basically safe. You only need to continue the surveys.
Yeah, so maybe coming to this topic of asteroid mining or utilization, I have 4 questions here. Asteroid mining companies like Planetary Resources or DSI have had a boom a few years back. They are now incredibly quiet of small autonomous satellites with AI. It moved somehow.
Yeah,
Why?
moved,
Where is it? So asteroid mining companies, Planetary Resources or DSI, have had a boom a few years back. They are now incredibly quiet. What happened to those corporate partners? Maybe that's a question to Fritz.
Which one now you have?
The second one.
Second one.
The second one on the screen. Sorry for...
Yeah. Yeah, clearly it was a very new idea 4 or 5 years ago. Some companies got early investment, limited amount of money, and they started their work on it. But in a way, they are now beyond the phase of announcing. They already start working on it, and it's a complex system. So just to define the ways there, what technology need, how to survey the asteroid, so to do the prospecting. The next step is then to decide which tools, what resources can be found, also in a direction how these resources will be used. So in a way, let me say, it's a complex task, and they work hard on it. On the other hand, they still try to get more money. So there was early investment, but not really continuous investment. So it is, like often in industry, you have to have a long pace and to really be patient, work hard in order to get there. So you're right, it got quiet, but it continues.
Yeah, exactly. And maybe one more point to this. Many of these companies, not necessarily those that have been mentioned, but it's sort of like the startup culture, new companies with bright young people having these great ideas and exciting the investors to get the early investments. But exactly, space activities, space industry, it's different a little bit in terms of how long does it take to mature the technology and to actually get to doing something. So it's also about the patience of the investors to explain them that this could be highly beneficial, but it is a long-term shot. You cannot expect to get the return of investment in a normal time span as doing your business on Earth, so it's about this as well. So then the company may have been unfortunate because the investors will pull out, no longer interested.
I think that's true, that it's a long-term effort to go there, which brings us to further questions here on the screen. So maybe the last one on the screen first. Do you think we will see asteroid mining activities during your, maybe Ian's, lifetime? So let's say within the next 2, 3, 4 decades maybe. So is this a realistic timely horizon that we will see activities on asteroids? What do you think?
I think it's hard to say because, I mean, intuitively I would say it will take a lot of time because, as I said, we know the knowledge is poor, we have very poor access to the composition from the Earth, etc., etc. But, if I take computers, if you have told me, when I got my PhD in 1997, my PhD advisor made me a great present, a 1 gigabyte hard disk. It was awesome. I was so happy, 1 gigabyte hard disk. If you could tell me that 20 years from there, I would have like 1 terabyte in a flash memory disk, and from 1 gigabyte to 1 terabyte, I cannot even compute. So it's very hard because the technology goes so quickly that I would say I'm happy to be deceived. One difference, though, is that space is complicated. It's very complicated. And that's why it's great also, it's exciting. So I'm not sure we can apply the same extrapolation we had with computers with space business, but I'm ready to accept that it will take less time than I anticipate.
And maybe you also can
maybe I would offer a slightly more optimistic
no, I said I'm happy.
Perception, because I think we're focusing on this topic a lot on asteroids, but let's not forget there's also a big lunar community.
Yes.
And I think when I interact with this community, I always try to merge the two. They still seem not to talk to one another. I'm struggling to get the lunar and the asteroid community to talk about resources utilization together because they share a lot. Clearly, the digging, the processing of the material will be different, but the underpinning technology will be the same. And with the new vision to go back to the moon and so on, I think there will be a lot of research in institutes, in laboratories that will develop this technology. So we still need to. Companies still need to learn how to go to deep space. This is not easy. Going to deep space requires today a lot of infrastructure on ground. So we need to develop those technologies that will enable new companies to operate maybe in a more autonomous way, have more intelligent satellites. So there's still a lot of work to do, but I'm convinced I will see it in my lifetime. If I have 1 second, I would actually like to answer also the other question, which is a bit tricky. I will not enter in the selection of the science mission. I think the competition in the science mission is extremely, extremely high. But there's one thing I've noticed working on asteroid missions in the last 12 years, is that the asteroid community is not yet federated. When there used to be Marco Polo, they would go to the Marco Polo proposal, then there's another concept, some of them go, and if scientists don't have their own instruments on board, they're not so interested. So I think my message there for the asteroid community in Europe, it needs to federate. They need to push together. When you go to a Martian conference, thousands of people are all pushing for whatever mission is on the table. Same for other planets. The asteroids are like asteroids. They're scattered, and therefore they lose political weight. So my recommendation to answer this question is that the community should federate. And that's why it's so important that missions make their data freely available, because that's the only way scientists, although they're not maybe a PI of an instrument, can benefit from each mission. And let's not forget, we are all taxpayers. And if we finally manage to implement a European mission, all the taxpayers should be able to get the data.
Yeah, thanks a lot. I think we could
In the
talk
way
on
mining starts at the moment, Hayabusa will bring material back. So it is in the gram or milligram range. Nevertheless, it demonstrates already in a very simple scale it can be done. I think it's, just to add on this, it will be at the end a mixture of investment, credibility of the concepts, and regulatory framework. I think this is very important, that also politics follows this. Regulation shall not follow innovation. It has to be in parallel to innovation and adapt permanently. Otherwise, I think the most breaking effect may be at the end the investment due to lacking regulation.
Yeah, thanks a lot. So I wanted just to mention, okay, we're really at the end of our time we have here today. It's a very interesting topic where I think any individual of you could elaborate on for an entire day or week. And I think we've touched a lot of aspects which are there. I think anyway it's a manifold topic or discussion point, so with many different aspects, and I would like to thank first the audience for all these interesting questions we had there. Unfortunately, we could not answer all of them, so still a long list which is available there, but maybe will give you the opportunity to have a, let's say, final statement from your side, short, precise. What is your perspective maybe on this topic, asteroid threat or opportunity for the next couple of years?
I should. Okay. Yeah. So I think I see the most important point to bring science, institution, industry, and politics together. And at the moment, we always have 3 in a club, in a meeting, and not all 4. And this is something everybody should push for to do it. And then I think even in my age, I'm the only gray-haired here, may have the chance to see some mining on planets and a defense system.
Jakob?
Yeah, threat out opportunity. We definitely have opportunity to build on this threat that is there, definitely. And, you know, it will be very simple when people ask me what kind of research we do, and I reply, planetary defense, asteroid mining. They're like laughing and asking, it's like science fiction. And I'm usually replies, do you remember dinosaurs? They didn't have a space program.
Yeah, thanks. Patrick?
Yeah, I would say that I think we live an exciting moment with the missions which are going on, because small bodies are really exciting. They are a laboratory for the scientists. If you are interested in science and you go in small bodies, you won't be disappointed. It's really great. Now what I want for the future is that also Europe make a mission also. And we have the excitement also from everywhere in the world, JAXA, NASA, ESA working together. And I think this is very important. I hope the ERA mission will go through, because it's a small mission, but despite the smallness of the mission compared to classical science mission, it addresses planetary defense, but it has a huge science return as a bonus. And I'm sure that young people who will want to go in this field will highly benefit from this mission as a European component in all this international interest to small bodies.
I think mine will be very short. I would suggest that next time we take a coffee, an espresso, this 34 cents, we think about it, and we invest it to make the HERA mission happen and bring the data to the scientists, to the engineers, and to industry who eventually want to make a business out of it.
Yeah, thanks a lot. So thanks also to you as an audience listening to us, providing all your valuable questions here. And I hope that you will take this discussion with you, spread it amongst the others, all the other participants here, but maybe also outside of the space community. And I think the main thank you is for our 4 panelists here supporting this activity and bringing in a lot of interesting aspects on this very manifold topic here. So thanks a lot for being here.
And thank you to the moderator.